Thank you very much. It's really a pleasure to be here presenting the work that we have been working on for the last 15 years of my life dedicated to this stuff that I'm going to show you in the next 45 minutes or so. Before I get started, I want to contextualize what I'm going to present to you. As Sunshine mentioned, our group is interested on looking at global patterns on biodiversity. We are losing species at rates beyond rates that we have seen in the last millions of years. Species are being lost. That's happening right now. So our goal is to figure out first how many species are being lost and what are the drivers of that loss. So we have research on all of those different components, and what I'm going to show you today, given the interest of working on climate change, is to show you some of the results of the projects that we have been doing about climate change. So that being said, the presentation today is about human vulnerability to climate change. An alternative title to this presentation is We Are Screwing It. What's going on here? All right, there you go. Oh no, but I don't like this, it's not playing. All right, so it has to be timed, though, so I'm gonna put a lot of animation there. All right, one of the important things that we all are probably very aware of is the importance of the climate on biological and social systems. Species, as included, we have been evolving characteristics that can only exist within a very narrow range of climatic conditions. As climate change comes along, we're going to be moved from that comfort zone. You can never expect anything good from climate change because it's moving us away from the comfort zone that we are used to. That is the response that you are going to see on species, but also in people. It turns out that we humans, we are also dependent on goods and services that we obtain from biodiversity. Food, water, air, those things we obtain from those species. So as those species get impacted by climate change, indirectly, that's going to impact people as well. So I hope you appreciate the importance of the climate, not only for species, but also people. Since the Industrial Revolution, one of the major changes that is happening is this massive increase in greenhouse gases. These gases, we know, are increasing the temperature, both on land and in the ocean, are also changing patterns on rainfall. Some places are getting dry, some places are getting wetter. It's also increasing sea level rise. The ocean pH is coming down. And there are many other interrelated climatic variables that are changing. All of that as a result of the increased emission of greenhouse gases. Of course, given how strong biological and social systems depend on the climate, it turns out that we also have very good evidence to suggest that these responses are already happening. For species, these changes in the climate, oh yeah, there you go. So as you change the climate, we know species are going to start moving. Species are going to be faced with three options. Some of them are going to move, all right? Right now, it's too hot here. I'm going to move to a place where it's colder. One of the major changes that you see there are species now, for instance, moving up north. Some species, they don't have that chance. Like, for instance, all of those species in small islands, what are the chances of moving? They are stuck there. They cannot move, right? But there's some other species that are going to move. Species in the continental areas, most likely they have the chance of moving. Unfortunately, there's going to be a bunch of species that cannot move and have not the capacity to adapt. For those species, the last option that they had is to go extinct. Those are the only three choices that a species will have when they are faced with climate change. As we impair the capacity of these ecosystems to produce food, well, it turns out that indirectly, we are also going to be impacted. There are also very direct impacts of the climate on us. Here, in this part of the United States of America, you are probably very aware of the increasing cost of damages triggered by the climate, right? However, there are also going to be impacts on health. There's going to be an increasing transmission of diseases, but more importantly, climate change could kill us. You know, you might think that this is an exaggeration, but climate change can kill us. To give you an example, in Europe in 2005, 50,000 people died because of a heat wave. And you might think, you know what, this is just one situation. And actually, that's exactly what I thought. And now with my students, we came to realize that there are hundreds of scientific papers reporting heat waves that have killed people. And they are all over the United States as well. Chicago, in Illinois, California, moments in which the climate moves beyond what people is used to, and people die. So this is something that is another consequence of these changes in the climate. Of course, another consequence, just as for a species, is that many people will be forced to move. Imagine, for instance, Mexico and the United States. That's a very good example. If agriculture in Mexico stopped being business because it's too dry, and you have to spend a lot of money for agriculture, what is going to happen to all of the people that right now is employed in the agriculture sector in Mexico? There's going to be a huge increase in unemployment there, and most likely these people is going to go where the chances are, which is most likely the United States. It's the same situation in other cases around the world. Indonesia, for instance, is predicted to lose a lot of the coral reefs. As those coral reefs get lost, the revenue that people get from those coral reefs, like jobs, are not going to be there. So that's going to force people from Indonesia to move to the closest place where they might find a better job, and that is going to be Australia. Bangladesh is predicted to be one of the countries most impacted by sea level rise. These people from Bangladesh is going to be forced to move to the next country, which is India. In that specific case, to make matters even worse, these people have completely different religions and they don't like each other. So you get a picture of the consequences and ramifications of this climate change on biological and social systems. Unfortunately, this general understanding of climate change, we don't have it yet. The reason is very simple. Here, you have physical scientists, right? This is people that is hardcore at physics and mathematics and put numbers to everything, right? This is the people that develop this very complex Earth system model. Now, here, you have the social scientists. Social scientists are people that go and fill surveys and ask you what you think about this. Completely different data, right? In one case, you have numbers. In the other case, you have opinions. And on top, you have the ecologists. The ecologists, we don't really want to deal with this complexity of the climate. This is just too hardcore for us. And we don't really want to deal with social scientists because we're not used to their data. So how do you integrate these completely different fields, right? Unfortunately, this articulation of this different field is fundamental to make a difference regarding climate change. Only when you are able to have a comprehensive understanding of climate change, you can start thinking about solutions, either on the mitigation side or on the adaptation side. Only this general understanding will allow you to identify what is the best solution to deal with climate change. And there is where my question for this presentation is today. How vulnerable are we to climate change? I'm going to present 3 papers that we have published in the last 2 years. So they are the independent case studies. The first one is about the impacts of climate change on marine biodiversity and people. All right? Again, all of the key words are on that title. Climate, which is physical sciences, ecosystems, which are the ecologists, and people, which are the social scientists. This is one of the first examples in which all of those 3 fields of research were articulated together. Now, we also feel some important gaps in our understanding of climate change. When we think about climate change in the ocean, some of the main variables that we think about are temperature and pH at the ocean surface. But it turns out that there is more to climate change than just temperature and pH, like, for instance, the oxygen and the ocean productivity. And the ocean is a 3D space, so what about changes in the climate on the deep sea? Of course, you have biodiversity. These ecosystems are located all over the world, and they're going to be in places that perhaps they might or might not be affected by climate change. Now, you have people that is depending on this biodiversity, food, jobs, and revenue. So, to what degree is these goods and revenues being impacted? And of course, you have people, and different people have different levels of resilience. The United States, for instance, I think is a country that is going to be very resilient to climate change. The main reason that we are pretty rich. Everything comes down to money. When the bad things will happen, I think that there will be a massive investment for resilience. So this doesn't really matter what happened here. I think that we will be very resilient. But you cannot expect the same for a country like Haiti, right? If climate change is to impact Haiti, these people is really going to be in bad shape down there. So this is what we wanted to do in this specific project, is to understand all of these systems all together. For this, on the climate side, we use Earth system models. So this is an example of an Earth system model. Before I play it to you, I want to show you what this is. This is the difference on temperature between that year. Is there a pointer on it? So, before I do something wrong, out there. So, what this map is the temperature between this year, 1950 to 1955, that's the average of that year, compared to today, right? So back then, and that scale goes from -4 to +5, 6, right? So back in this day, 1950, the world's oceans were a lot colder than what they are today, right? And that line there, that black line, is the global average. So this is just one of the models. So you can see how there is some annual variability as time goes by there. The interesting thing is when we hit the new millennia here. You can see now there are some hot spots over here, over there. And as soon as you get to the 2000s, now the planet starts warming up. You can look at the global average, now how this thing goes up. There you get these massive hot spots of very high temperatures. And this is the expected temperature by the year 2100. At the global scale, a massive increase of 3 degrees in the world's oceans. This is just one of 40 models that we analyze. Every model is run under 3 different emission scenarios for 100 years, 12 months, 365 days, for a total of 60 million maps, right? For just one variable, and we analyze 12 different variables for these things. So you get the picture of how big these databases are. So here I'm just going to show you the results of 4 climatic variables that are going to be changing in the ocean: temperature, oxygen, pH, and phytoplankton productivity. So this is just the change between today and the year 2100. For instance, under this scenario, you can see that the planet, by the year 2100, is going to get very, very hot in many places. In some places, hotter than 5 degrees Celsius. Oxygen is going to be depleted pretty much everywhere in the world, with the exception of these places over here. pH, every single place in the world is going to be more acidic. And phytoplankton, there are going to be some places in blue here that are going to see an increase in phytoplankton, and some other places where you are going to see some decreases in phytoplankton. So what we did, we took these changes and we scaled those changes from 0 to 1. 0, meaning the smallest changes that we see, 1 being the largest changes that you can see. These allow you then to put all of these maps of change in the same map. It's like a cumulative score type of thing, and this is the cumulative score. It ranges from 4, which is the largest change on any of the 4 climatic variables, to 0, which is places where there is no change whatsoever in any of the variables. What is remarkable about this map, though, is that there was not a single place in the ocean where there was nothing changing. While there might be some places that the temperature might not change, those places are going to be hit by acidification or reductions in oxygen. So it doesn't really matter. There is no safe place in the ocean for these poor species. Either they're going to be hammered for one thing or they're going to be hammered for another thing. Now, let's bring the ecological data. We have now global maps on the distribution of different ecosystems and people, and what we did, we overlapped all of these maps, about 40 maps that we had on the different changes, and what we did just was to quantify the average change in any given climatic variable on that ecosystem. This is the figure that we obtained. There's a lot of data on this figure, but actually it's pretty simple, the message here, because the message is pretty consistent. Before, let me explain to you the axes here. This is the temperature. All of the axes are centered at 0. For instance, in temperature, seamounts are going to see a very small increase in temperature. Seamounts are very deep in the ocean, so the changes in temperature are not going to be very hard, very big there. But you can look at, for instance, coral reefs here. In red, which is temperature, coral reefs at the global scale might be warming by about 2.5 degrees. When you look at oxygen, sorry, phytoplankton, the phytoplankton is not so bad. Oxygen, there is going to be a decline of about 0.2 milligrams per liter. So basically, what it means is that if you are below this line, changes on the ecosystem are going to be negative. If you are above that line, that means that the ecosystem is going to be impacted by some positive change in the climate. But what is remarkable from that is that all of the ecosystems in the world that we analyze, 32 of them are below this line, meaning that all of them are going to be impacted by changes on any one of those climatic variables. Reductions in carbon, pH, oxygen, temperature, every single ecosystem. There's not one ecosystem that is lucky enough to be in places where climate change is not going to happen. Now, what about people? This is where the social sciences come in. What we did, we have global maps on the distribution of people as well. We overlap those maps with changes in the ocean, right? And we just counted the number of people that is living close to areas where climate change is going to be very intense. We ended up coming out with this number that at the global scale, there is 1.4 billion people that are living in places close to the ocean where the ocean is going to change quite dramatically, right? This is just exposure. 1.4 billion people are going to be exposed to high changes in the ocean, in the supply of those goods and services from the ocean. Of those, 690 million people had high dependency on the ocean. This is people, mainly from islands, where everything depends on the ocean. The food that they get, the jobs that they obtain, even the revenue of the country depends on things that you obtain from the ocean. And finally, 470 million people, of those are poor. That's the most vulnerable people in the world. 470 million people that are living in places that are going to be highly impacted by climate change, had a high dependency of the ocean, and to make matters even worse, they are poor. You might think this number is not so bad, 470 million people. The problem is that this is under the low emission scenario. This is if we start dealing with climate change by tomorrow. Under the business as usual scenario, which is the projection in which we are, you ended up having double the number of people that is going to be vulnerable. 870 million people in the world today are located on places that are going to be highly impacted by climate change, high dependency on the ocean, and are poor. This is the most vulnerable people in the world as a result of climate change in the ocean. This paper was the last paper in a series of papers funded by the Census of Marine Life and an initiative that is called INDEEP. I was part of a group of 23 scientists, and this paper got published in the journal PLOS Biology. Let me move on to the second case study, and this one is now moving to the terrestrial component. I wanted to find out, well, okay, I found that the human vulnerability to changes in the ocean, but what about on land, right? This project actually got started after I had an argument with a climate denier. And the argument of this climate denier was this: climate change will be good for plants. That's the argument. Climate change is going to be good for plants. And I was fired up by that comment. As you can imagine, I just came out from this study saying that close to 900 million people is going to be impacted by climate change, and this guy comes along and says, no, climate change is fantastic. Plants are going to grow nicely there. What I discovered was that he was right. The reason of this argument is this. In the scientific literature, there is something that is called the growing season. The growing season, scientifically, is defined as the number of days in a year that are above freezing, right? Of course, if climate change is happening and the planet is getting warmer, there are going to be a lot of places that are going to get warmer, especially here at mid-latitudes. So there is going to be more time for plants to grow here at mid-latitudes. And indeed, there is a lot of research being done on this. This is just one of the examples of a paper published in Science showing how, for instance, at mid-latitudes, there are going to be a lot of places where there are going to be more days above freezing. And what that means is that indeed plants are going to have more time to grow. So I was just thinking, oh my God, this guy was right. But then I realized my basic courses in biology when I was an undergrad, and I realized that there is more to plant growth than just temperature. Turns out that plants, of course, they need temperature that are above freezing. If it is freezing, they're not going to grow. But it turns out that there is also an upper threshold to temperature, in which if you exceed that threshold, the plant is going to die. Right? So why is this definition doesn't include the upper threshold of temperature? But that is just thinking that temperature is the only factor that influences plant growth. It turns out that you also have water. You need a certain amount of water for you to grow as a plant, and you also need radiation. So I thought, you know what, this is an opportunity to write a new paper to redefine what growing season really means. What we ended up doing was this. We took global maps that are generated by satellite imaging and some very complex models that allow you to calculate the amount of plant growth that occurs anywhere in the planet every day. It's called net primary productivity. So we already have very good data that can tell you at the global scale how much biomass plants are generated on specific places, right? So I took that data and I overlapped that with daily data on temperature, radiation, and soil moist. Soil moist is an indicator of water availability, how much water is available for the plants to grow. We put all of these maps together, and then we do these things that are called frequency distributions. Basically, what we do here, for a given day, we calculate the amount of biomass that is produced at the global scale as a function of temperature. At the global scale, 95% of the biomass that is produced by plants is produced between 3 degrees Celsius and 30.8 degrees. For radiation, it's between this limit and that limit, and for water, it's between this limit and this limit. And we generated this new metric that is called suitable growing days. This is a new term that we are using for this paper. And basically, it's the number of days in a year that are in these thresholds, which we identify are thresholds in which plants can grow. Basically, what we wanted to find out is whether that number is going to change in the future or not. So let's look at the comment that the climate denier was saying, that climate change is going to be good because there are going to be more days above freezing. It turns out that he was pretty right. You can see that map there. This is the number of days above freezing by the year 2100. And you can see how by 2100 you are going to have a lot of places, especially at high latitudes, in which there are going to be fewer days below freezing. Since warming is happening, indeed there are going to be more days that are suitable for plants to grow. But as I mentioned to you, temperature also has an upper threshold, in which if plants cross that threshold, they die, right? That's what happens when you bring that second threshold. What you ended up finding here, though, is that in the tropics, all of these areas here are actually places where temperature is going to get hotter than what the species can tolerate. And indeed, this is what is massive about this discovery, I think, the fact that in some places, especially in the Amazon and all of these places over here, you might be losing up to 200 days for plants to grow. Just think about this. I mean, I don't know if you are farmers or whether you had some tomatoes in your house, but you realize already by looking at the simple reaction of plants that they need time to produce the tomato, right? What we're talking about here is that now you are shrinking the number of days that that plant has to grow that tomato, up to 200 days in the tropical areas. Plants are not going to have time to grow. Even if you have more days above freezing at mid-latitudes, in the tropics is where things are not going to go so great. And of course, when you bring the other thresholds in water and radiation, the pattern doesn't change at all. You still have the tropical areas having fewer days that are suitable for plants to grow. These here are the global averages over time And these are the different criteria that we use. This in blue, here, this dotted line, is the number of days at the global scale that are above freezing. And as the climate denier was saying, there are going to be more of those days. Indeed, that under that definition, the growing period is going to increase by 6%. By the year 2100, the growing period, based on just the number of days above freezing, is going to increase by 6%. But when you bring the upper threshold of temperature and the thresholds for water and radiation, it turns out that what you ended up finding is that at the global scale, the growing season is going to shrink by 21%. Now, there is something very interesting about these patterns as well, because look at what's happening here. Do you see how the capacity of the whole planet to be more effective at producing food by the year 2100 and the climate change is restricted to Canada, China, and Russia? Can you imagine becoming vulnerable? The food supply is going to be controlled by China. I mean, that will scare anyone. And I mean, actually, I will think that perhaps this is their plot to have climate change going on. Because for them, and the Russians and the Canadians, according to this analysis, are the only ones in which you are going to see some benefit on climate change being suitable for plants to grow. Everywhere else, you are going to see massive shrinkage in the amount of time that plants will have to grow. And that right there. And of course, this is under the business as usual scenario. This is the pathway in which we are right now, which is to do nothing. However, if you repeat the analysis, under a strong mitigation scenario, these are the results. There's no change whatsoever. Meaning that we had a mechanism, we had a pathway in which many of these things can be prevented. Now, as I mentioned to you, one of my interests is also to look at ecosystems. What are the responses of ecosystems? Here you can see the amount of days that different ecosystems are going to lose. For instance, mangroves and broadleaf evergreen forests, they're going to be losing up to 100 days on temperature. Meaning that for many of those ecosystems, there's going to be fewer days that are suitable on temperature. And of course, when things get too hot for many of these tropical ecosystems, what happens is that these tropical forests start to die. We already had a lot of evidence suggesting that that is indeed happening. Now, there is also something very interesting. Like these ecosystems that are at higher latitudes, like the permafrost, you can see under this scenario, for instance, there are going to be more days above freezing. However, what is not happening there is that there is no change in light nor water. Usually what happens on those places is that all of the carbon that is storage on that permafrost gets locked. Right? It's like a bank of CO2. Any CO2 that lands there gets frozen on that permafrost. But as the planet starts warming up, which happens every year, all of that CO2 gets released. But the plants are there to pick it up again. They pick it up, and at the end of the summer, the leaves fall on the ground, and the carbon gets stuck, and it never leaves, right? That's the natural process. But one of the things that is happening here, though, is that temperature is warming up, meaning that the permafrost is going to be melt, the CO2 is going to be released, but you have no water, no radiation, meaning that these plants are not going to suck that CO2. This is one of the major concerns on the scientific literature these days. The extent to which climate change is going to unleash these carbon bombs that are storage on all of these ecosystems. Today, just on the shallow part of the soil, we have 400 pentagrams of carbon stored just in permafrost. And of course, the implication of this is the extent to which these changes are going to accelerate climate change even more. Another climate feedback here on these ecosystems that are going to be facing higher temperatures is that maybe they won't die. But they can change photosynthesis, which is taking the carbon and bringing it down and turning that into proteins, to respiration, which is actually producing CO2. Forests can turn from things that take CO2 to now things that actually release CO2. So that can actually accelerate climate change even more. Now, what about human vulnerability to this? Here are the results of that. At the global scale, we had 3.6 billion people. Isn't that a mind-blowing number? 3.6 billion people that are living in countries where there is going to be a massive reduction in the number of days that those countries will have for plants to grow. Of that, 3 billion people have high dependency on agriculture, and 2.3 billion people are poor. This is the most vulnerable people in the world to just changes on land. This is the global map of vulnerability. In red, meaning the most vulnerable countries in the world, and in blue, meaning the less vulnerable countries in the world. One thing that you can appreciate from this map is that there is no country in the world that is blue. So I now need to make a break here, tell you something personal about me. Like, as part of the Census of Marine Life, we were used to have a lot of money to do this kind of stuff. The Census of Marine Life was like our sugar daddy for doing research. Anytime that we needed money, the money was there to do it. But they say, okay, this is it. We're not going to give you any more money. And the problem was for people like me, pretty young people that had no credentials to start getting money. And I found it pretty hard to get money from anywhere to do this kind of research. To make matters even worse, I was drowning in teaching. Of course, I got a job as an assistant professor, and I was very proud until I realized that I needed to go and teach. And now I need to get grants, and I need to apply for tenure, and I need to show these things. But I'm not getting publications because I don't have money, right? So I figured, what do I do here, man? I am up for tenure pretty soon. I had no publications to show because all of my time has been invested in teaching and writing grants that have been unsuccessful. So what I decided to do was this. I went to my students and I said, look, guys, I'm going to be honest with you. I had a paper that I think we can publish in Nature. And I want us to do this project together. The idea of this project is that you are going to get all of the skills necessary to write a paper. And that's the course. How do you get to understand methods to publish papers? And I'm going to be honest with you, and of course going to get a paper out of this. And we are all going to be co-authors on that paper. And that worked perfectly. Because we started working on this paper as part of a class. And the thing that they didn't realize, though, is that I actually was getting free labor as well. So it was like a win-to-win situation, you know? I was fulfilling my requirements for teaching. I was fulfilling my requirements as a scientist because I was getting papers, and to make matters even better, I was getting the best reviews of the whole department because the students were getting papers out of this thing. And this is one of the students in the class. Here we are. This is a paper that we got in review in Nature. Now let me tell you the last case example, which is about time. We think about climate change, and we think about the magnitude of change, 2 degrees increases in temperature. What that means, you know, like how do you relate to 2 degrees change in temperature? But I think that you can relate more easier to time. If I tell you that tomorrow climate change is going to come, whoa, you know? So we developed this new index that we call it the year of climate departure. Let me explain the index to you. Imagine this location here, which is actually Hawaii. And here is the temperature in Hawaii. And we start measuring that temperature in the year 1850. This is the variability that people in Hawaii has been seeing in temperature for the last 150 years. There are some places some years that have been pretty cold, and some times in which it has been pretty hot, right? We took those 150 years, and we define the limits of climate variability as the minimum and maximum temperature that the people in Hawaii has seen in the last 150 years. This is the extremes, the coldest or hottest that you have ever seen, right? Then we took the model simulations, and we calculated the year at which the climate moved beyond anything that you have seen. This is a year when the climate is going to be beyond anything that you have seen in the last 150 years. In this case, that year is the year 2029. In Hawaii, by the year 2029, according to this model, temperature is going to move beyond what people have seen in there for the last 150 years. And we define that year as the year of climate departure. That is just for one location. Now let me show you all of the locations in the planet. According to the strongest mitigation scenario, the global average year of climate departure is 2069. And under the business as usual scenario, that year is 2047. And of course, there is some variation there. By the year 2047, according to this model, the planet is going to move to a new state of temperature. When it's even worse, the soonest changes are going to be happening on places again that have poor capacity to respond. Here, we overlap our timing of climate departure with the number of people, and we just counted the number of people according to the year in which temperature is going to become completely abnormal for them. What we found is that by the year 2050, 1 billion people, according to this model, and 5 billion people, according to this model, are going to be living in places where temperatures are going to move beyond historical records. To make matters even worse again, those countries are located on the poorest countries in the world. Here we related the timing of climate departure against gross domestic product, and you find these two interesting relationships, regardless of the emission scenario, in which are the richest countries in the world where climate change is going to come last. Isn't that sad? That the people, the countries that are contributing the most to climate change are going to be the ones facing climate change last. Another remarkable thing of this paper, though, that I find is that most of us, we are going to live to see this. You know, when you think about climate change, the rhetoric is we are leaving a legacy for our children, our grandchildren. We are going to live to see that. Listen to this. According to our analysis, by 2020, climate departure is going to be happening on tropical areas, and 2047 is the global average. This is just 34 years into the future. Right now, I'm 39. In 34 years, I'm going to be 72. So there it goes, Camilo. I hope you like it hot. That's my legacy to you. We have been doing this thing at a global scale, and one of the other problems that we are having with climate change is failing to make people relate to climate change. We think for some reason that this is something that is going to happen somewhere else. One other thing that we're trying to do as part of this analysis is to bring this data to the scale of people. You can go to the webpage of my lab, just look around, and there is this map there where you can zoom in to your house, click on the button, and you can see the timing of climate departure from the place where you live. And we were hoping that with that, people can get a better sense of connection that when is this going to happen where you live. Again, as I told you, I'm trying to do this as a part of a course for grad students. Of course, I ended up spending long times with my students. And in fact, my partner, she probably thinks that I'm having an affair. The reason for that is that I spend so many time with these students. Sometimes we start at 8 in the morning and we finish at 3 in the morning. And I show up home at 3 in the morning, right? And it looks kind of suspicious, really, every single day for you to show up at home at 3 in the morning. And then my partner, she says to me, hey, honey, what is this? 3 in the morning. I was just like, honey, I'm teaching class, right? So it is not only suspicious that you are showing up at 3, but you had a terrible excuse, really, to show up at 3 in the morning. But we had a great time. It truly becomes like a team that we can pull out things together. And in this specific case, we actually got a paper in Nature, one of the biggest scientific journals, and we were able to pull out a paper there just with students. Last section, though, I had 2 last slides. I'm not going to tell you how to face climate change, but if you want, you can ask me later for the discussion. But I'm going to tell you 2 reasons for why we need to do something. The first reason is this. We are taking these ecosystems today from ecosystems that look like that to ecosystems that look like this. Things like climate change, habitat loss, overexploitation. There are multiple reasons why these ecosystems are being transformed this way. What is dangerous about this transformation, in my opinion, is the possibility that these changes might never be reversed. That is as a result of something that we have discovered that is called alternative equilibrium states. It's a very scientific term, but let me bring it down to you. The population of a species is there. They are adapted just to live there, right? All of the life histories are adapted to be there. Now, things like overexploitation, habitat loss, climate change, they come along, and now the species try to adapt to that new condition. By adapting, what it means is also that you're going to be losing some genes. Once those genes are gone, they are gone for good. What it means is that if you were to remove all of the threats, the species cannot go back there because it's missing the genes. Actually, what we had evidence for is that instead of recovering, there is a chance that this species actually could continue down the hill on a process that is called an extinction vortex. Species, the individuals become so rare that they don't find each other to mate. The genetic diversity becomes so low that they can be completely driven to extinction by a hurricane. And the ultimate pathway on this is extinction. Down this pathway of population decline is extinction, and extinction is already happening. Here is a paper that we published in Science last year. We take a relative proportion of the number of species in the planet. You are up here at this line, which is 75% of the species going extinct. That's classified as a mass extinction event. We went through the literature and we took all of the data on rates of extinction, and what we found was this. The rates of extinctions of all of the papers range between this value and that value, and what that means is that by the next century, the rate of extinction of a species is going to be equal to the rate of extinctions that we have seen in the last 5 mass extinction events. Humanity could take pride on being among the top 5 most extreme events that have driven over 75% of the species to extinction. Extinction is already happening. Let me just give you a blink of the species that we have driven extinct in the last few years. This species went extinct in 1981. This one, 2011. This one, 2004. This one, 1970. This one, 1930. This one, 1970. 2010. These are species that you will never see again. This one, 2010. This one, 2011. This one, 1741. You get the picture. And just like that, some 20,000 species driven to extinction every year. And you know what is sad about this? That many of these species we will never know, because we are only describing 8,000 species a year. Many of these species that go extinct, we will never know. So going back to my thing, and I have a few minutes, that's the last slide. As we impair the capacity of these ecosystems, what is going to happen is that you are going to lose the capacity to produce food, important goods and services, and that ultimately is going to impair human welfare. For us, this is not a big issue here because every one of us here, we had breakfast, lunch, and dinner. But today, we have 1 billion people in the world that are hungry right now. So you have to wonder, how are we going to improve the quality of life of these people when we are triggering this set of actions and reactions that is impairing the capacity of those same ecosystems to provide food? There is a second reason, and this is the last slide of this presentation. The second reason is that if this planet goes wrong, we are stuck with it. The global or general understanding of the universe has revealed that we know on the order of about 100 billion planets that look like our planet. Of those, only 10 have the characteristics of planet Earth. That means that the probability of us finding another planet like ours is 1 in 1 billion. Let me just contextualize that number for you, if you don't mind. Does anyone here knows anyone who has won the national lottery once? Okay, good. Actually, somebody one day say, yes, I won the national lottery, and it completely screwed up the analogy for me. All right, but this is what 1 billion means. 1 in 1 billion means that you will win the national lottery 5 times in a row. Not 5 times in your lifetime, 5 times in a row. We don't even know a person that has won the national lottery once. What are the chances that you or I are going to find a person that will win the national lottery 5 times in a row? This planet goes wrong, we are stuck with it. Now this is the last slide. And I had to conclude by saying that we already know all of these things. Everything that I told you already scientifically has been demonstrated, not only by me, but by many other scientists. So I had to conclude with a remark that I heard on a movie by Benjamin Franklin. and that remark there. We are all born ignorant, but one must work very hard to remain stupid. We already know this stuff. With that, I thank you very much and have a good day.